Have you heard about a method to make qubits using stuff called quantum dots or something like spin qubits? And are lost in the several papers and articles on this subject? Well, we get it. Today, let's focus on demystifying this subject and making it more intuitive. There are different techniques that can be used to prepare the physical qubits for our quantum computers that rest at the physical layer or on the quantum chip of our quantum coprocessor. Different techniques include spin qubits and quantum dots, which make use of semiconductor methods, transform qubits, a type of superconducting charged qubits for reduced sensitivity to noise, NV center qubits, trapped ions, and the list goes on and on. So basically, the material we use in context of a quantum technology is the quantum material. A quantum material provides the environment for our quantum. So as we will discuss later, the two-dimensional electron gases of gallium arsenide, silicon-28, silicon germanium are a quantum materials in case of spin qubit. A quantum material should allow easy spin orbit coupling and ensure long spin coherence time. And usually this is a trade-off in the current era, but we need to fight this in order to make scalable quantum computation a reality. Now that we know what a basic quantum material is and its requirements, let's proceed to understand quantum spin qubits. Quantum dot spin qubits have relatively longer coherence time than other qubits, which allow for a faster performance and smaller chance of error during computation and readout. To provide you with its industrial relevance, Intel, the chip giant, bets on this technology to make its qubits. Let me clear this right from the start. Spin qubits are generally related with the semiconductor industry and not the superconducting industry. In the current classical chips, the semiconductor industry plays a vital role. The most fundamental part of these chips is the transistor. Now, what is a transistor? A transistor is a switch controlling the flow of electrons between two contacts using voltage applied to a single gate. Now, how does a transistor work basically? A transistor has two contacts, the source and the drain, and between them lies the channel, which allows the electron to move through it from the source to the drain. Above the channel lies the gate, which is a metal electrode. The positive gate voltage attracts the electrons into the channel so as to allow a conducting path from the source to the drain. The negative voltage, however, empties the channel so that no current can flow. You can imagine we name the flow of current as bit 1 and no current as bit 0. You good till here? Awesome. Now that we understand what a transistor does, let's proceed to see how we use this model for our quantum bits. For that, instead of 1, let us have 3 of these metal gate electrodes. Let's say I keep gate 1, gate 2 and gate 3 with a positive voltage for the first 10 seconds. Then I decide to flip the voltages of gate 1 and gate 3 to negative. What happens? You see, the electrons isolate in small puddles from the rest of the world below gate 2. This is exactly what a quantum dot is. A quantum dot is a small space where electrons are pulled in below one gate and are separated from the others. There are many properties of these quantum dots. Therefore, it is an active field of study with several applications. But for our purpose, it's sufficient to think of quantum dots as described here. The quantum dot spin qubit manufacturers try to produce such quantum dots that have only one electron in them, and the spin of this isolated electron is going to be a quantum bit, that is, the qubit. The operations on the spin qubit are conducted at low temperatures using the dilution refrigerators to ensure that the thermal energy is lesser than the charging energy. More about charging energy in the coming parts. The gates shape the electric potential landscape and the channel. The negative potential of the gates form the potential barriers that separate the contacts from the quantum dots and also separate the quantum dots from each other. These barriers must have sufficient potential to control tunneling. There are various configurations of a qubit: the loss-given sensor configuration, the singlet-triplet configuration, the exchange-only configuration, the quantum dot hybrid qubits configuration. The These qubits are initialized, operated, and measured in the same manner, but their ease of operation and robustness to noise varies. Several materials were tested for preparing qubits, but the first success came from gallium arsenide or aluminium gallium arsenide. This was used as a two-dimensional electron gas which was passed through the channel. Later on, it was found that this material suffered from decoherence during the operations, so we switched to silicon. Stick around to know more about this.